In sections 4.2 and 4.3, we're now going to use derivatives to identify behaviors that we're interested in for functions, maxima, minima, inflection points. And we're actually going to come back to some of the ideas that we had seen in Chapter 2. So there are a lot of definitions and theorems in these two sections, and I've put them all into this document. So we have the definition of an absolute max or an absolute min. That is a y value that is higher or at least as high, the highest the function goes on its domain. Now, FYI, in addition to the word absolute, you might also see the term global, that a function has a global max or a global min. And I want you to notice the word is here. So we could say f of x has a max or maybe a min at x equals c, or sometimes it'll say at c. But the max or min is f of c. So the y value is the actual max or min, but we often, very often, refer to a max or min by its location, which is what the input value is. Now, we also have local maxima and minima, and sometimes instead of the word local, you'll see the word relative, and I will use them interchangeably. And the same thing here, and we have the notion of near C. That means in an interval around C. So note to self, that means that a local max or min cannot occur at an endpoint. Whereas a global max or min can occur at an endpoint. And they have an example at the top of page 264 about this. So if the function is defined on an interval that's not all real numbers, there's some restriction there, then you can have a global max or a global min at one of those endpoints. But that would not be also a local max or min because the interval is not around the x value. It stops and only occurs on one side of that input value. So again, I strongly encourage you to read in your textbook pages 262 and 3. Look at the pictures that go with the examples 1 through 4. So then we have this extreme value theorem, and again, when it comes to theorems, having the conditions met is so important. So the function, in order to be able to apply this theorem, you have to have a function that's continuous on a closed interval. And if that's the case, then there has to be an absolute maximum value and an absolute minimum value somewhere in that interval, which, note to self, could be at the endpoint. And they do, as it says, make sure you read carefully at the bottom of page 264. That's where they give you some examples where the extreme value theorem appears to not work, but it's because the conditions are not met. So if the function is not continuous and or the interval is not closed, then the extreme value theorem does not apply. Now, this term extreme value is what we sometimes use to denote maxes and mins, we call them extreme values. All right, so okay, then we have Fermat's theorem, and again we have to be careful because it doesn't work in both directions. So if f has a local max or a min at c and the derivative f prime of c exists, then the derivative must be 0. Okay, and again I hope that you can picture that, and we're going to see a lot of pictures in these sections, so hopefully if it's not clear right now it will become clear. But note to self, just because f prime of c equals 0 does not mean that f has a max or a min at x equals c. And again, notice your book is saying local max or min at c. So the input value is where the max or min occurs. The max or min itself is f of c. So, but again, just because the derivative equals 0 doesn't mean you automatically have a max or a min. But if you do have a max or a min and the derivative exists, then the derivative must be 0 at that max or min, assuming it exists. Okay, then we have the definition of a critical number, and one of the key things you want to notice here is in order to be considered a critical number, that value, and again it's an input value, has to be in the domain of the function. If it's not in the domain of the function, then we can't consider it a critical number. But critical numbers are places, input values in the domain where either the derivative is 0 or it doesn't exist. So I put in here the different things that might happen at a critical point. If the derivative does equal 0, then you might have a max or a min there. If the derivative's undefined, you might have a sharp turning point. And in your book on page 265, they show the absolute value function as an example. It's got a minimum value at x equals 0, but the derivative is undefined at x equals 0. That would be a sharp turning point. And another thing that could happen where the derivative is undefined is you could have a vertical tangent line. Now, number 6 here, statement 6, if f has a local max or min at c, then c definitely has to be a critical number. Again, it doesn't work the other way around necessarily. You could have a critical number that does not correspond to a max or a min, but if you do have a max or a min, then that place must be a critical number. All right. Now we have a first derivative test. So one of the things we're going to be using our derivatives for is to find maxes and mins on functions. And so if you have a critical number at x equals c, and your function is again continuous, then you can determine by looking at how the behavior of the first derivative changes. Well, not behavior, the sign, S-I-G-N, of the first derivative changes, whether you have a max or a min or neither. So, for example, part A here, we have C a critical number, and let's say f prime changes from positive to negative. That means f must change then from increasing to decreasing. So again, remember from chapter 2, if the derivative is positive, then the function is increasing. Where the derivative is negative, the function is decreasing. So you can see if f goes from increasing to decreasing, then you have a local or relative max at x equals c. In part B, say you have your critical number at x equals c. If f prime changes from negative to positive, then f changes from decreasing to increasing, then you must have a local or relative minimum at x equals c. And part C, if the derivative does not change its sign, so say f prime is positive both to the left and the right of C, then the function increases on both sides, so you have no max or min at that spot. All right, then, again, remember what we learned about concavity back in Chapter 2. So we can look at concavity through the first derivative being increasing or decreasing. So if f prime is increasing, then the function f is concave up. If f prime is decreasing, then the function f is concave down. We can also look through the second derivative. If f double prime is positive, then f is concave up. Where f double prime is negative, then f is concave down. Now notice this says for all x in that interval. So in other words, there's a place where potentially the function changes its concavity. It's neither greater than 0 nor less than 0. It's equal to 0. Then that would not be included in the interval of where the graph is concave up or concave down. Now we can use the second derivative also to check for maxes or mins. For example, in part A here, they say if f prime is equal to 0 and f double prime is positive, then f must have a local min at C. Why should that be? So we have a horizontal tangent line, the slope of the function, is 0, but the function is also concave up. Well, if the function is concave up, and you have a horizontal tangent line whose slope is 0, then you must be talking about a minimum. Similarly, in part B, if we have a horizontal tangent line, that is f prime of C is 0, and f double prime is negative, meaning the function's concave down, then it must be that you have a local max at x equals C. And then remember, again, this from Chapter 2, a point of inflection is a point, again, it's got to be in the domain of the function, where the function changes its concavity. So we can look for those where the second derivative either equals 0, this is missing an S, where the second derivative equals 0 or is undefined. So what you want to do is look at the sign of the second derivative on either side of a possible point of inflection. So for example, let's say f double prime changes from negative to positive, positive to negative. That means f changes from concave up to concave down, which means we must have an inflection point at C. So we're looking for the second derivative to change sign. It's possible that the second derivative could stay the same sign on either side, and then there would not be an inflection point. And then we have the closed interval method. So if you want to find an absolute max or min on a closed interval, again, the function has to be continuous. You can find the critical numbers and then also evaluate the function at those critical numbers and at the endpoints, and whatever value, whatever output is the largest is your absolute max, and whatever value output is the smallest is the absolute min. Okay, and last but not least, where else can a function change its behavior? It can change its behavior at a place where the function is actually not defined. So the graph could change its concavity on either side of a place where it's undefined. It could change its behavior, say from increasing to decreasing or vice versa. It doesn't have to change its behavior, but if you're going to be analyzing a function completely, which is what we're going to learn how to do in these two sections, then you have to make sure that you check the behavior on either side of a value where the function is not defined. Okay, and then critical numbers and points of inflection have to be places where the function is defined. So if the function's not defined there, you can't call that a critical number. There can't be a point of inflection.